So we start one of our last subjects in mechanics with the idea of universal gravitation. And what we mean by that is the idea that any two objects in the universe attract each other with a gravitational force. Now, we've seen a little bit of this already, in classic mechanics. So far we've seen, okay, an object's falling, it experiences a force mg and has a potential energy of mgh. And what's kind of interesting is that force doesn't seem to depend on where you are. You could be down here, up here. It's always mg. It's always the same. That turns out when you zoom out and get on a big enough scale not to be the case anymore. So let's consider two objects separated by a considerable distance in space. We'll call them M1 and M2. It turns out that they do attract each other, that they experience a gravitational force toward each other. And this is again what we mean by universal gravitation. Every object in the universe attracts every other object in the universe. And they do so with a very particular force that looks like this. So the force of gravity in general in the universe is not actually just mg. If I have two objects, it actually looks like this. Big G, m1 times m2 over r squared. Now there's a couple things to note here. First of all, what is big G? Big G is a fundamental constant of the universe equal to 6.67 times 10 to the negative 11th, and it has units of newtons times meters squared over kilograms squared. In any case, times 10 to the negative 11th is a very small number, which is befitting the fact that gravity is actually a very weak force, unless you have very, very large objects. You take this number, big G, you multiply it by the product of the two masses, and you divide by r squared. And I just want to note that this distance r is measured center to center. So sometimes you do have to consider, for instance, how big an object is. It's from the center of one object to the center of the other. To give you an idea of the scale of this force, let's run some little examples. Imagine that I've got, imagine that I've got two objects that are just 1 kilogram each, right? 1 kilogram, 1 kilogram. And let's say that these are floating in space and they're 1 meter apart. So two objects about a meter apart. Well, considering that all of these numbers are going to be 1, the force of gravity between them that each one experiences would be then 6.67 times 10 to the negative 11th newtons. So what? 0.123. So an extremely small force between them. And I do want to note, of course, that Newton's third law still applies. That is the force on this one. It's also the force on this one. So an extremely tiny attraction between them. On the other hand, if you consider, say, the sun and the earth, right? The mass of the earth is rather larger, 5.97 times 10 to the 24th kilograms. The mass of the sun, of course, even bigger, 1.99 times 10 to the 30th kilograms, nearly a million times bigger. And the distance between them does vary. It does vary, but on average, it's about 100 and, what would that be? 150 million meters. No, 150 billion meters. Yeah. In any case, if you go ahead and calculate the force there, despite being 150 billion meters apart, the Earth and the Sun pull on each other with a force of 3.52 times 10 to the 22nd newtons. So a 3 followed by 3.52 followed by 20 zeros. So an enormous force. So just to note, gravity is interesting. At normal masses, it's tiny. But when you get up to objects the size of planets and suns, it can be very strong. It can be very strong. There's another important thing to note here, which is this over r squared. And this is not the last time this year we'll see this. notice that the force of gravity varies as 1 over r squared. So what this means is that, let's say I have two objects and there's some distance r apart. And let's say at that distance this one feels a force F. Well, if I pick it up and I move it another r away, if I double the distance, think about what happens. If I double the distance between them, 1 over r squared, my force gets cut to 1/4 of what it was before. If I go out to 3r, it's F over 9. If I have my distance, right, if I come in here, all of a sudden my force gets 4 times stronger. So this is what's called an inverse square relationship. And that's a really important concept. If I double my distance, the force of gravity gets cut to 1/4 of what it was before, 1/4. So very, very, very important. What about mg though? Like, I've told you all year that gravity was just mg. What about that? Well, that's still fairly true. So let's take a look. Here's the Earth, right? And we're going to put an object very, very, very close to the Earth. We're going to put an object very, very, very close to the Earth. And we're going to drop it. And we're going to ask, well, how does it fall, right? I want to note, first of all, that this object, let's call this an object little m, and the Earth here has a mass of big M. And of course, we can also still, it might behoove us to know what the radius of the Earth is, all the way down to the center of the Earth. Note, by the way, this doesn't necessarily have to be right on the surface, but as long as we're fairly close to the surface, right, if we're some distance h above the surface, as long as that distance h is very, very small compared to the radius of the planet, we don't really have to worry about it too much. So let's look at the force on this mass, right? Well, it's going to be big G times big M times little m over r squared. But I want to note, if I pull out the little m, I end up with this quantity that only has to do with the planet. And this is, in fact, what we call the gravitational acceleration, g. So I'm going to put it back over here, that little g, the gravitational acceleration somewhere, is equal to big G times the mass of the planet times how far you are from the planet's core, squared. Big Gm over r squared. And this does work, by the way, if you calculate this for Earth and you plug in the mass of the Earth and the radius of the Earth. And if you want to, for those of you playing along at home, the radius of the Earth is about 6.37 times 10 to the 6th meters. If you go ahead and calculate this g for the Earth, you end up with a very familiar number. If you do 6.67 times 10 to the negative 11th times the mass of the Earth divided by the radius of the Earth squared, you get 9.81 meters per second squared. If you try this for Mars, by the way, and I'd like you to take a moment and try this for Mars. The mass of Mars is 6.39 times 10 to the 23rd kilograms, so it's, about 1/10 the mass of Earth. The radius of Mars is 3.39 times 10 to the 6th meters. So see if you can figure out what is the gravitational pull at the surface of Mars. Well, if you've done your calculations properly, you'll get 3.71 meters per second squared. So the gravity on the surface of Mars is quite a bit weaker than the gravity on the surface of Earth. One last thing that comes up quite often, there's more things that come up quite often, but one last thing that comes up quite often is the idea of putting something into orbit. So let's say, here's my Earth, and let's say I wanted to put a little satellite into orbit, right? Here's my satellite. Satellite. Whoop. Let's get my satellite in a color that actually works. Here's my satellite. And for the moment, I'm going to assume we want to put it into a circular orbit. We'll talk a little bit more in the future about what happens with non-circular orbits. But let's say I want to put my little satellite of mass little m, Earth is of course a mass big M, and I want to put it into orbit at a radius of r. And reminder, that radius is measured to the center of the Earth. Well, you might notice that I've drawn a circle here, and as I have often told you throughout the year, circles can mean only one thing, which is that it's time for centripetal force, because if this satellite is in fact going to go into orbit, it needs to be traveling with some velocity v, and it needs to have some centripetal force. So what's providing that centripetal force? Well, most of you would naturally say gravity. G big M little m over r squared is providing that centripetal force. But of course, if it's in orbit, that also means that that centripetal force is little m v squared over r. A simple manipulation gives us this really, really, really important result. That the orbital velocity of something in a circle is root g m over r. Notice it doesn't depend on the satellite's mass, it only depends on the planet's mass. It also varies with radius. The further away you are, the less fast you have to go. So if I try this, by the way, for the ISS, and the key thing here is that the ISS is an additional 400,000 kilometers, or 400,000 meters, excuse me, above the surface of the Earth. So you might have to do a little bit of addition. If I calculate this for the ISS at 400 kilometers above the surface of the Earth, I get about, as near as makes no difference, 7,700 meters per second. Note that this is about Mach 22 relative to the speed of sound at sea level, which goes to show the big problem with space is not that it's very far away. This is a really bad scale drawing. The International Space Station is actually much closer to being like this. 400 kilometers compared to the size of the Earth is nothing. But the real problem with space is not that it's far away. Many of you have probably been on a trip further than 400 kilometers. It's that you have to go really fast to stay there. So the orbital velocity that you need is quite high. We're going to do more in our next video that has to do with energy. So we'll talk about escape velocity, gravitational potential energy, and things like that. Before we go, though, I want to note, as for the exam, they give you this equation. And I actually think they give you the potential energy equation and a couple others. They give you this equation, they'll give you this constant. However, they do not give you the equation for little g, nor do they give you the equation for orbital velocity. So you need to either know these equations or know how to get them. For instance, if you forget the equation for orbital velocity, hopefully you can remember that it's a centripetal force equation. So you set gravity equal to the centripetal force and solve for v. So that is really important, that in this little unit, there's a lot of equations that we're missing. This, by the way, is the number that you need, the speed that you need, well, this equation. That's the speed that you need to stay in a circular orbit. Most orbits, though, are not purely circular. So if you go too slow, what happens is that you end up in an elliptical orbit. And if you're going too slow, your elliptical orbit will get closer to the planet. If you're going too fast, you'll end up in an elliptical orbit where the other side of your orbit is further away from the planet. So we can talk a little bit more about that. Elliptical orbits are something we talk about only kind of conceptually in this class. But next time we'll talk about energy. We'll also talk about Kepler's laws and do a quick demo of all three of Kepler's laws, at least for circular orbits.